Oh. Is that working now? Nice. Okay, so I'm going to pray that this is working. And just get started. Wait, I should make sure we have audio, huh? Check. Hey. Ah. Okay, so it's working. So we're going to start with question 9. So we have a government survey. And 20% of employed women have never been employed. Sorry, 20% of employed women have never been married. Okay. So we should define success then. Success would be a woman who hasn't been married, right? Employed woman who isn't married. And so we don't have a sample size here. So for 9, no sample size yet, right? No sample size. No hint of first success. So this really isn't anything yet, is it? Okay. X would probably be equal to the number of employed women. For binomial. X would be equal to the trial number of the first employed woman for a geometric setting. So, just on first reading, I'm not quite sure what they're looking for here. It's not really anything. Yeah.
For the binomial one, wouldn't it be number of employed women who aren't married?
Employed women. Right. Unmarried, let's put it that way.
Okay.
Unmarried women. Unmarried. Good point. So it really depends on what the next question is going to be.
Why did you put 2 X's? Why is one for binomial and geometric? It didn't ask for 2.
Is it geometric?
It doesn't ask. It just says, is it binomial, geometric, or...
Yeah, because that X changes depending on which setting we're in. If we're talking about the binomial
it's
setting.
It's asking if the setting is binomial, normal, or geometric. It's not telling you to...
Yeah, we don't know.
Do both. Okay.
And yeah, the fact that we don't have a trial number kind of leads me to believe that this is going to be a geometric setting. Okay, because for binomial we need to have a set number of trials, and there's none of that here. So if we go to number 10, however, things kind of change. Because now we say there are 10 women selected at random. What's the probability that 2 or few have never been married? Okay, so now we have something. We have a set number of trials. We have 10 women. The probability of success is 0.2 because we're looking for unmarried women. And we're asking, what's the probability that the number of unmarried women is 2 or fewer? So that reads to me like less than or equal to 2. So that's a binomial CDF. If we can count all of or if we can just kind of state all of the outcomes which would make this true, which outcomes are less than or equal to 2. 0, 1, and 2. So that's the probability that x equals 0 plus the probability x equals 1 plus the probability x equals 2. Then, you know, you ignore all that and grab your calculator.
0.678 or 0.6778.
Yeah.
6, 7, 7.
Right. And so from the calculator, you said 6778? 6778.
On the test, do you want us to show that p of x is less than the greater than 2 equals?
Yeah,
or
if
equals
you're
0, blah, blah,
listing
blah?
4 or less
Numbers.
outcomes. I don't want you to get ridiculous with them. Okay. Question 11. What's the mean and standard deviation of x? Well, now that we know x is actually this one, the number of unmarried women, now that we know that, we can get a mean and standard deviation. So mu is equal to NP. N is 10. And P is 0.2. So our standard deviation is 2. Or our mean is 2. Our standard deviation is equal to the square root of N times P times Q. So Q is 1 minus 0.2, which is 0.8. Okay, 12. Find the probability that a employed woman who has never been married, or the number of employed women who have never been married, is within one standard deviation of the mean. Okay, so the first question we need to ask is this a normal distribution? No, it's not. It's a binomial distribution. So we can't really use methods of normal curve. So not a normal distribution. Do not use norm CDF. What we should do is figure out what is within one standard deviation. Within one standard deviation means mu plus sigma to mu minus sigma. I should probably put that the other way around. Okay, let's figure out those numbers. What is mu minus sigma? Mu is 2, right? So 2 minus 1, 0.265. That's mu minus sigma. Mu plus sigma. That's equal to 2 plus 1.265 equals that. Okay? All right, so then what we're trying to find out is what's the probability that the number of women is between these two numbers, between 0.735 and 3.265. Well, there's no such thing as 0.735 women, right?
Right.
So we have to kind of, do we round that up or round that down? Round that up. So we need the probability that x is less than or equal to. Rounded up, that's 1, right? So less than equal to 1, or greater than equal to 1 and less than equal to, should we round this number down or up?
Down.
Down to 3, good. Down to 3. So every number between 1 and 3 would actually be between 0.735 and 3.625. Which outcomes are we talking about?
Probability that
X equals 1 plus probability X equals 2 plus probability X equals 3. So we just need to add these 3. Okay. That's a little bit tricky on the calculator, isn't it? How would we do this? Would you use CDF or PDF, do you think?
PDF. Just
Oh.
do the
Probably the easiest thing to do is PDF here, right?
Yeah, just do
3 PDFs. Yeah, there is a way to do CDF as well.
4 and then minus 1.
3 minus okay, so 2 things we could do. We could do binomial PDF 10.21 plus binomial PDF 2 plus binomial PDF 3. That's one way to do that. Or, let's see, we need it to be less than or equal to 3, right? So that's a binomial CDF 10.23. But we need to get rid of 0. So minus binom PDF 10.20. Both of these should get us to the correct answer. What is that correct answer? $12. Wait, this is answered completely differently, isn't it?
Yeah.
Let's get this answer though.
I got 0.7716. I want 8, sorry.
7718.
That's what I got when I did the binomial CDF one.
Okay, they should both be the same. Okay. And remember, this is using a sample size of 10. The way that you see in 12 in the answer guide is kind of assuming that you can use a normal distribution. You don't have to use a normal distribution if you have the sample size. Okay. 13. Describe the 4 conditions. What are our 4 conditions? Number 1.
There's 2 options.
Good. Two outcomes. 2. Probability of success. Does not change. 3. Outcomes are independent. And 4.
Set number of trials.
Set number of trials.
What is the first one you guys did?
2 outcomes. That means success or fail. Next. Okay, so survey conducted by the Harris Polling Organization discovered that 63% of Americans are overweight. I really did look that up.
Can I go to the bathroom?
63% of Americans are overweight. So let's write that down. So this sounds like we're saying success is an overweight American.
You wanna put number 14 on it?
Yeah. This is for 14 through 19, right?
Yeah.
So success, I should put that in quotes because that's not really success, is it? Unless you want to be an overweight American.
You want to be an average citizen.
Oh, who wants to be average?
Above average.
Above average. Yeah, clearly. Okay, so 30 students at a particular Sunday school class are questioned about their weight. Assuming that this is a good cross-section of Americans, show that the binomial conditions are met. Okay, well, we just wrote those down. So we can just kind of put those in there and show that they are. So there are two outcomes, success and overweight, or success and fail, yes. There's overweight and not overweight. Does the probability of success change, stay the same?
Yeah.
Yes. 65%, right?
Yeah.
63? My bad. Okay, are the outcomes independent? Yeah.
Yeah.
Yes.
Me too, looking at like
We'd have to kind of assume this, but you know, having one fat American child will not, sorry, overweight American child will not affect whether the next American child is overweight, right? You have to kind of say that yeah.
Eating habits do not transfer.
Eating habits.
Can you say independent?
I want to use independent to kind of justify independent.
Shared.
Eating habits are unrelated between separate.
Oh, unrelated between citizens. Do you really believe that?
absolutely not.
No.
No, I don't really believe that either. But for the sake of this, let's just say yes. Do we have a set number of trials?
Yeah.
Yes. There are 30 students. So it seems as though we have ourselves a binomial distribution.
Did you get a question on someone's test? By any chance?
Like what?
Like this? Like, did you
Possible.
have to put all these 4 points
Possible.
on an AP test as well? Or?
Probably not. That's our binomial situation, 30 and 0.63 binomial setting.
Is that part of, like, when it asks you, is the form?
No, that's not part of it. That's just for,
It was there.
just because, you know, it's kind of appropriate to put it at this point, I think. 15. What are we asking in 15? Find the probability that 18 or more of the 30 students are overweight. Yeah. It's a probability that, okay, so, sorry, we should also put X is equal to the number of overweight students.
On the test, if we have that stated in the clause A, do you have to rewrite that?
No,
because then
no.
you-
Once you write that B30 and X equals the number of overweight students, then you don't need to write it again for all parts.
Okay. And also remember you wrote like x is b30, comma 0.63. Do you have to write stat or just?
Yeah, that's going to be a better way to write this. Okay, so we want to know 18 or more. So 18 or more, that would be greater than or equal to 18, right? Okay, so we can't really compute greater than 18 on our calculator, except I think the TI-89 does, right? Yeah, pretty sure it does.
It would.
So we need to turn this into the complement of the set. So we need to do 1 minus. So let's see. The numbers that are greater than or equal to 18 are 18, 19, 20, 21. So the other numbers would be ending 1 through 17. So we need the probability that x is less than or equal to 17. Yeah.
Does that include 0?
That includes 0, yeah. And then it's calculator. And let's see, second distribution.
A while ago.
Yeah.
Where is
30 trials, 0.63. And we want to go less than or equal to 17.
it?
2945.
1755. No, when you subtract the,
Yeah.
you gotta subtract it from 1.
Yeah. 7055. 16. Show that the normal approximation can be used for a sample of 30, and then use the normal approximation to answer question 15. Okay, so let's see. If we can use it for sample size 30, that would mean that NP has to be greater than or equal to 10. And NQ likewise must be greater than or equal to 10. Don't forget to check NP and NQ every time. NP is, what is that, 30 times 0.63? Okay, that's equal to 18.9. That's certainly greater than or equal to 10. No. And let's check the other one. 30 times, what's Q here?
137.
Yeah, 0.37. 1 minus 0.63 is 0.37. That's 11.1. That's definitely greater than or equal to 10. So we're good to go. We can use a normal approximation. Okay, so let's do that. Our normal approximation, we need a mean. The mean is 18.9. And we need a standard deviation. That's equal to the square root of 30 times 0.63 times 0.37, right? It's probably more digits than we need. Okay, we want to know greater than 18, right? So the z-score is going to be equal to 18 minus 18.9 divided by the standard deviation. That's going to be the z-score, negative 0.34. Okay, now that we have our z transformation, we're going to say the probability that x is greater than equal to 18 that's equal to the probability that z is greater than negative 0.34. And that's calculator time.
Just for
Hmm?
since so x is greater than 18 or greater than or equal to. Oh, if it was less than, would you have to switch the sign on 18 minus 18.9?
One more time.
So what if it was x is less than or equal to 18?
Mm-hmm.
Would
Di-
you have to switch the top part?
No, no, this is what would change right there.
Okay.
The z-score, this calculation for z-score is always the same. Number minus mean over standard deviation. Okay, so we want to see the probability that x is greater than equal to negative 0.34. So now we use norm CDF, negative 0.34. Infinity. Zero and one. You get 0.6331. Now, another way that you may want to think about this, I don't know if I want to muddle your head with this too much, but another thing that would be accepted is if you also computed the z-score for 30. Because we have to be less than 30, right? That's 420, right? And because we really want to calculate the probability that x is less than or equal to 18, and then also less than or equal to 30. So that's the probability that z is between negative 0.34 and 4.20. Now 4.20 is a really high z-score, so that's not really going to change the answer too much. Let's do that on the calculator. Change that to 4.20. If only this calculator was more responsive. .6631. Wow, it's the exact same thing, right? Either one of those work. Some people feel like this is more appropriate to the situation. So, depends if you're one of those people or not. Okay. What's the probability that it takes more than 5 attempts to find an overweight person? So now we're switching scenarios here, right? The setting has switched to a geometric setting. Am I skipping something? Oh, this is 17. Okay. Since we are looking for the first overweight person, student. So how many So we have a geometric setting. Probability of success is 0.63. X is going to be equal to the trial number of the first overweight student. So the mean is 1 over p, which is 1 over 0.63, 1.58. So we would expect to I don't know, how would you say this? We would expect to find? We would expect to
Spot.
Yeah, you said fine.
okay. We find the
Oh,
first
we would expect to weigh 1.6. That's what you wrote
Oh.
down.
let's change that. On average, it would take approximately 1.6 students before we found the first overweight student. On average. Oh, I see what you're saying. You're making a fat joke, aren't you? 1.6 people. Wow.
No, no, no.
You're so insensitive.
I was not making a joke like that. It's saying like you have to see 1.5 like regular people before you
Can't
see
fix
someone
it.
overweight.
Regular people should not.
Overweight people are pretty regular too.
Under people who are not.
This is why we can't have good, nice things. 18. What's the probability that it will take 5 or more attempts before an overweight person is found? So now we want to say the probability that, well, 5 or more, that would mean x is greater than equal to 5, right? That's 5 or more. Okay. And so I'd like to go with the way that I think is better here. If it's gonna be 5 or more, how many failures do you need to make that happen?
5 or more. Or
Well, the first person has to be not overweight, right?
yeah.
Second person has to be not overweight.
Yeah.
Third person has to be not overweight.
Yeah.
Fourth person has to be not overweight. How about that fifth person? Does he have to be
They
over?
can be.
Can or can't be, right?
Yeah.
Could be overweight. So actually, we only need 4 failures.
The question,
It says
doesn't the
more than
question
five.
just say more than 5?
Does it say more than 5?
Yeah. It's more than 5 attempts. to
Oh,
find
more
it.
than 5. Okay, so then that fifth person has to be a failure, right? So that's how many failures? 5?
Yeah.
You need 5 failures. 0069.
Just for
Yeah,
that's including the minus p. The 0.37 is 1 minus 0.63.
yeah,
Okay.
yeah. That's the probability of failure. Wait, which number is this? Is this 18 now?
Yeah.
And 19. Oh, yeah.
When do you multiply, like, the Q times the P?
The only time that I think we've done Q times P is to find the norm. I mean, the
Like, it has, Q,
standard deviation.
Q to 1 power times P.
Oh,
to 1
oh,
power.
oh. Yeah.
That's what I'm talking about.
Yeah, that's if you want to. That's for a CD or a PDF. If you want to know the probability that we find the first overweight person
Or the second
in the
most
third
likely.
interview,
Okay,
that would be Q times P.
got it, okay.
And so, what's the last one? 19. Construct a cumulative distribution table. Stop at n equals 6. Okay. Okay, so cumulative distribution table means we have to make a distribution table to start off with. So what is the regular distribution table?
You stay geometric or
Yeah, we're still saying geometric.
X and B.
So yeah, we need x. No. X. 1, 2, 3, 4, 5, 6.
You always start at 1.
Yeah, because we're doing a geometric. 0 doesn't make sense for geometric. Like it, we would never find the first overweight American in the 0th trial. So the probability that x equals x. Okay, so that's going to be just success, right? It's going to be failure times success. This is going to be 2 failures. Q squared times P. This is going to be 3 failures, right? Cubed times P. This is going to be 4 failures. And this is going to be 5 failures. So I'm purposely just kind of leaving these in here, leaving those there so you can see how to compute that. Let's do the first one. The first one is 0.63, right? 0.63. Now the second one, we're just going to take that 0.63 and we're going to multiply that by failure. 2331.
that's cumulative.
Yep.
Yeah.
We have to do this before we can get to cumulative. Though.
Oh.
This is a regular distribution table. All right, so the next one, we need to multiply this result by another 0.37, right?
I got a 0.08.
Oh, wait, 624.
Yeah.
I'm going to do another one, and then I'll just have you guys read them to me. Then multiply that by 0.37 again. Chalking up another failure, that's 0.319. And then,
0.01181.
okay, and then
0.0044.
0.044.
Yes.
I don't know what I just did there. .0044. Great. So that's just a regular distribution table. For the cumulative distribution table, we need to add everything together to the left. So, cumulative distribution table.
What do you mean to the left?
We'll just do that so you can see what I mean. So it's kind of starts the same way. We have x, 1, 2, 3, 4, 5, and 6. But instead of the probability that x is equal to x, we want to know the probability that x is less than or equal to x. This is what makes it cumulative distribution. Okay, so what's the probability that x is less than or equal to 1? 0.63. Probability that x is less than or equal to 2.
Is that 0.2331 plus 0.63?
Exactly, 0.63 plus 0.2331. And how much is that? 0.8631? And the probability that x is less than or equal to 3, that would be this one right here for 3 plus 2 plus 1. So let's just shortcut that and say it's 0.8631 plus 0.0862. Why did I leave the 4 here? Sarah, what'd you get? 9.5. Anything else?
9493.
9493.
That I did in the house.
394. Yeah, 9493. And then just go ahead and read off the rest of these. What are the rest of these? Yeah, it's rounded to 98, isn't it? Yeah.
0.9812.
Okay. 99. So you can see, like, for a cumulative distribution table and a geometric setting, the probability keeps on increasing. Yeah.
Can you do number 4?
Yeah.
Yeah, that one's.
Quick question about this. Is this, can this be represented by an OJ? Is that what this is?
You could do an ogive. If you graph this out, it would look a lot like an ogive, yeah.
Okay.
But usually an ogive is not meant for something that's open-ended,
Okay.
like it is. This is like this just keeps on going. All right. So the choice of the people is number 4.
Yeah.
Okay, number 4. Okay. Suppose we get an SRS of sample size 100 from a large population with p successes, p proportion of success. Let x be the number of successes in the sample. For what value of p would it be safe to assume that the sampling distribution is approximately normal? Well, you know a couple things that have to be true about p, right? P, n times p has to be greater than 10. NP must be greater than or equal to 10. And NQ also has to be greater than or equal to 10. Well, we have n already, right? N is 100. So 100 times p has to be greater than or equal to 10. So that means that p has to be greater than or equal to 1/10.
Yep.
0.1, right? So that's one requirement. The other requirement is NQ, right? So 100, and I'm going to change this from Q to 1 minus P. That also has to be true. This also has to be greater than or equal to 10. Okay. And if that's true, that means 100 minus 100p has to be greater than or equal to 10. Yeah? And when you solve that out, you're going to get p has to be less than or equal to 90, or 0.9. So these are the two things that have to be true for the case where you have 100 in your sample size. So, in summary, why are you still bold? No. In summary, for sample size 100, p must be between 0.1 and 0.9. Now this was from a multiple choice question where the answers kind of got separated. But if you looked at the answer choices, the only one that would work, where p is between 0.1 and 0.9, was 1/11th or 1/9th. Yeah,
The whole test is calculated.
yeah.
What?
Every test,
What did you say? What?
the whole test is calculated.